Hello everyone, it's Benny, and welcome back to the Ultimate Guide to Redstone. In this video, we're going to continue our discussion of logic gates, and we already talked about the NOT gate and the OR gate, and hopefully everyone has a pretty solid understanding of those. But now we're going to move on to the AND gate. And the AND gate isn't another one that's really not that hard to grasp the concept of. So the AND gate, the only time it turns on is if both inputs are on. And the reason it's called the AND gate is if A and B, that's the only case you get the output. So really, it's not that hard to grasp the concept. It's just only if both inputs are on, that's the only time the output's on. Otherwise, the output stays off. And that's the AND gate. Not too hard, hopefully. It's not that complex of a concept. Oh, and I almost forgot. That is the code of B8. And if you want to know more about what the code business is all about, look in the last video. I explain it there. But yeah, hopefully not that hard. And now we're going to talk about how to build it. Alright, so let's talk about how to build an AND gate. Now, there's quite a few designs for AND gates out there, but unfortunately a lot of them are kind of tricky to understand the logic that's going into it. So I'm going to start with a design that I think is the easiest to understand. So, it starts like this. Here's input A, right here, and not a piston, but lever. There's input A. Okay. Now, to get the output, there's the output. All you have to do is you connect input A to the output, like this. And there. Now, input B goes right here. And what input B is going to do is, instead of connecting to the output, it's going to connect to a piston. And that piston is going to have a block right there. And if you look, this behaves just like an AND gate. If I hit A, nothing. If I hit B, nothing. If I hit both, output. So, this is probably the easiest design to understand. Because what's happening here is simple enough. If I just try to flip input A is the only wire that's connected to the output. So that's the only thing that can possibly power the output. But if I flip it by itself, then that can't power the output because there's a block in the way. So if I just flip input A, it does nothing. Now, input B. Input B is not connected to the output, so it can't possibly power the output. But if I flip it, it does activate a piston. And that piston pushes a block out of the way. And with the block out of the way, that means input A can now connect to the output. And this is a reason it can only work if you have both input A and input B. If you don't have input B, then there's going to be a block in the way, and you're going to need to power the piston to push the block out of the way. So I think that's the most, not the most basic, but the easiest design to understand. So, if that doesn't make sense, don't worry, there's a couple more designs, so one moment. Alright, so this design for an AND gate is probably a little bit more common, but it's also a little bit trickier to understand. And here's how it works. You start with input A, like this, and input B. So what I do is I take both of these inputs and plug them into NOT gates, like this. So now all I've done is I've inverted input A and I've inverted input B. And the neat thing about this is the only time that both of these wires right here will turn off is if I have both input A and input B. What this means is I can just plug these wires into an OR gate, and this will almost give me an AND gate. The problem is, instead of turning on when I have A and B, it's turning off when I have input A and B. But there's a very easy way we can fix this, and that is with an inverter. So just plug all that into an inverter, and now we have an AND gate. So with input A and input B, and the output. And hopefully that makes a little bit sense as to why that is. And this is using something called De Morgan's theorem, which states that any OR gate, i.e. this one right here, can be turned into an AND gate by inverting both input A, input B, and the output. It also states you can turn any AND gate into an OR gate using the exact same process. So if I took an AND gate and I inverted input B and input A and the output, it would turn into an OR gate. So that's De Morgan's theorem, and that's the reason why this works. And yeah, if you want to know more about that, you can just look it up on Wikipedia or something, or I'm sure you can find it somewhere. But yeah, that's the reason why this design works. Although it's not commonly built like this, it's more commonly built so that the NOT gates are going upwards like this, and then the OR gate is in the center, and then this is the output. This is the more common version of the same design. And yeah, so that's the AND gate, or at least how to build it. Now let's talk about when we're going to use this. So, one moment. Alright, so one of the most common uses of an AND gate is as a locking mechanism for your door. So right now, I have a door that's unlocked, so I can open and close it with a lever. But if I flip the lever on the other side, then it doesn't work. So essentially what this is doing is I need to flip one lever to enable the door to be opened, and then I can open and close it with the other lever. And the neat thing about doing it with an AND gate is that it works from either side. So if I wanted to, I could unlock it like this, and now people can open it from this side. Or I could do like this, and that would unlock it for people on this side. So that's one use of an AND gate. It's probably one of the most common uses. Alright, so another use for the AND gate is in my amazing invisible castle. So, last time we had our TNT cannon hooked up to an OR gate. And that meant that if either me or my friend saw someone coming, we could fire the TNT cannon at him. And that's great, but one problem is it causes accidental misfiring, so if either of us accidentally hit the button, all of a sudden we just wasted a shot. Another problem is if there was any dispute of or whether we should shoot them or not, either of us could override the decision and just shoot them anyways. So, another way we could do it is with an AND gate. This way, both of us have to agree to fire the TNT cannon and press the button at the same time. And only if the buttons are pressed at the exact same instant does the TNT cannon fire. So you notice I just tried pressing both buttons, and I can't fire the TNT cannon. But if I hit both of them, and I'll try to do it quick and see if I can register it. So if I hit both, that's too slow. Come on. It's too small of a target, come on. I can do it. Trust me. Nope. See, it's a very effective system. Okay, I can try to be a ninja here, alright? No. Hell yes. That's how you do it. Bam! And now TNT is shot off into the horizon, and now we've killed whoever happened to be standing in that exact location. And yeah, so there's another use. As you saw, it's very effective. It's not easy to hit the button for only one person, but yeah. So that's another use. So, that's pretty much the AND gate. Hopefully you understand it and why it's useful, because it's a pretty important gate. And with that, that's going to conclude the big three. The NOT gate, the OR gate, and the AND gate. These are the big gates. They're the ones you will see and use the most often. And if you cannot take away anything else from these logic gates, take away these. They are the most important. Now, there's also 4 others that you'll see pretty commonly, and the rest you really don't see that much. So this probably isn't enough to complete everything you know, but these will get you pretty far. So, yeah. And now, I'm going to just move on to the next gates. So, next gate is the NAND gate. It has the identification code of B7. This gate is a lot like the AND gate. The only difference is, instead of turning on when both inputs are on, it turns off when both inputs are on. So as you can see right now, it starts off being on, and the only time I can turn it off is when both inputs are on. So, very simple, but it does have a very important property that makes it much more important than the AND gate on some level. And I'll explain that after I show you how to build it. So, in fact, I'll just move over here. It's really easy to build. So we built the AND gate. I'm just going to build an AND gate really quick, like this. This made an AND gate. So it shouldn't be any surprise to you that to make this into a NAND gate, you just delete this. And it's magic, you have a NAND gate. That's pretty much the design you're going to see for NAND gates. It's not that hard. Sometimes you'll see one that looks like this, but this is pretty much the design for NAND gates. So yeah. And like I said, there's a very important property it has that makes it different than the AND gate, and far more important in some respects. And if you remember from the first video, I talked about I have this coding system, and glowstone is one of the codes. The NAND gate is a universal gate. What this means is you can use the NAND gate to produce any other logic gate that you want. So for example, if I wanted to use the NAND gate to make an AND gate, I'd build another NAND gate, and probably need a little bit further back. So NAND gate, and what I'm just going to do is I'm just going to combine the inputs. And I've made an AND gate from NAND gates. And yeah, and you can make any logic gate using just NAND gates. So that's one of the things that makes this really important, because if you have anything that you're not sure how to do, you'll want to try doing it with universal gates, if you're doing anything experimental at all, because you'll know that you can achieve what you want with universal gates. You don't necessarily know that you can achieve it with other gates. So that's one of the reasons why universal gates are important. And yeah, so that's the NAND gate. I'm not going to show any examples because it's pretty much the same thing as an AND gate in terms of practical use, except it automatically inverts it for things where you want an AND gate with inverted outputs. And yeah, but the important thing is you can build any logic gate out of NAND gates. They're very important. So, there you go. And on to the next gate. So next up is the NOR gate with identification code B1. This gate is a lot like an OR gate, but the only difference is, instead of turning on when you have any input, it turns off when you have any input. So it starts off giving output, and if I have any input on, it turns off. And this gate's really easy to build. I'm going to show you how to build it. So first off, you take a torch, like this, and then input 1, input 2. Done. NOR gate. And there. So now you've created a NOR gate. Very simple, very easy, and yeah. And as you saw with the glowstone, this is a universal gate, meaning, like the NAND gate, you can make any logic gate at all using just the NOR gate. So, needless to say, very important gate. But the NOR gate is especially important. And the reason the NOR gate is so important is because it comes essentially built into redstone. It's just the torch with 2 inputs. And the reason that's important is because this gate right here is the reason why redstone has all the power it does. Since redstone has essentially a NOR gate built in, that's what allows you to do everything you do with redstone. Everything you do with redstone is essentially a NOR gate used in sequence. So, yeah, very, very, very important gate. So, there you go. If you ever wondered why redstone was as diverse and powerful as it is, right here, the NOR gate. So, yeah. And again, it's a lot like the OR gate. It's just used in cases where you want the input or the output inverted. So, yeah, it's pretty much used in the same situations, except when you want the output inverted for whatever reason. So, yeah, that's why I'm not going to do any examples. It's pretty much the same usage as the OR gate. And yeah, so I'll move on to the next gate in the next video, because I think I've covered enough in this video. So, in the next video, I'll cover the next final 2 gates that you'll pretty much see. The rest of them won't see that much. And yeah, so hope you enjoyed, hope you learned, and see